So Rubén is a contributor to some libraries at Boost, and is a contributor of the C++ Alliance. And, well, he is going to talk about asynchronous input-output and coroutines. So the two things I want to really see working together.
And I promise it's easier than what it looks like. So
Good.
Thank you
Good.
for ruining my introduction. Yeah, I'm Rubén. I work at the C++ Alliance. I'm a staff engineer. And I am the author of Boost.Mysql. It's an asynchronous library to access MySQL. And it's written on top of Asio, and that's what we're going to be talking about today. So today I'm bringing you a tale about three things: coroutines, timeouts, and cancellation. I hope it's more a fairy tale than a nightmare, but who knows? So I acknowledge that this is not an easy topic, and I won't lie if I tell you this is easy. No, this is hard. But my first message is, please fear not. We are not going to be building things from scratch. We're not going to be manipulating coroutine handles or writing promise types. We're going to be writing code like the one in here. Like, that doesn't look really that complex, right? So what I want to achieve with this talk is that you can bring home like some basic concepts that you can apply in your day-to-day job. So something useful for yourself. And since this is like a complex topic, please, if at some point you get lost or you have questions, just raise my hand. I don't promise seeing you, but just making me notice, and feel free to ask, please. Feel free to interrupt me. Don't worry if you don't know what this means or you haven't worked with Asio before, because we are going to be going through from the basics and build up. Right? So before going to anything else, I always like remembering a little bit the differences between synchronous and asynchronous programming. So let's say I'm this guy, this developer, and I'm running my own program is synchronous. So my laptop is a bit old, a bit outdated. So I go to this to the shop and I order a new one. Unfortunately, once I engage in an interaction, since I'm in a synchronous program, I need to finish it because I'm using blocking functions. So this means that until the laptop arrives at home, I'm going to be sitting in front of my door waiting for the delivery guy for a day, which is not a very useful, it's not very useful, right, for me. On the other hand, if I had been running an asynchronous program, I would just close my tab and open my VS Code and start coding. And once the delivery guy arrives and notifies me, I would go to the door, pick the package, and continue with my life. So this is kind of an exaggeration, right? But this is kind of the difference between synchronous and asynchronous programming. Synchronous programming uses blocking functions, which means that if you are engaging in a long read, you're waiting for your client to send data, it's going to block until you have the operation completed. So it's going to need to create threads for concurrency. On the other hand, asynchronous programming is going to be based on events, so it's going to involve some kind of user-land scheduling. So this makes us to the first point there. Usually, asynchronous programs have behave better under heavy load, and this is because context switching becomes expensive when you have many threads. But we're not going to be talking a lot about performance in this talk. I want to highlight the second point. If you are in Asio, at least, asynchronous APIs are much more powerful. You have more functionality. So for those of you who have written Asio before, you can't, this is a blocking function, you can't set a timeout to that. You just can't. There isn't really a portable way of doing that. On the other hand, it's pretty trivial to write a timeout if I had been using a synchronous function. So this is the kind of thing we're going to be seeing. So my takeaway point here is if you're using Asio, prefer asynchronous APIs because they're getting much more simpler to use and they have more functionality. So for those of you who haven't met Asio before, Asio is a high-performance I/O library for C++, and it offers asynchronous primitives. If I had to define that with an easy quote, I would say powerful but complex. I like saying this is like a forest with many trees, and it's very easy to get wrong and to get lost there. So I hope to be your guide for this not to happen. These are actually two versions of Asio. There are two versions of Asio. There is one within Boost, which comes with the Boost distributions, and one which is a standalone library. Before going into details here, I want to run a little survey. Who has used in more or less real code one of these libraries before? Please raise your hand. Okay, quite a lot. Raise your hand if you have been using the Boost version and now standalone version. Do you guys know the difference between the two? So the point is, they're not forks. They are different libraries. Actually, they're incompatible. Like things live in different namespaces, but they are in essence the same library written by the same author. And what's actually happening here is that he has a Perl script that dumps one thing to the other. If you happen to find an issue, please report it to the standalone one. That's where he sometimes answers. Now, for the differences, they're almost the same library. The Boost one has some extra functionality and uses some different types for some things, but all what you are going to be learning in this talk are applicable to both. Now, there is something that I think is important, that is, there are these four libraries which build on top of Asio. The thing with Asio is that it's like a very low-level thing. So you have sockets, you have timers, but you don't have an HTTP request, for example. So these four libraries build on top of Asio and give you this extra functionality. So for example, if you need HTTP, don't choose standalone, choose Boost, because these four libraries just work with the Boost version. If you just need sockets and timers, you can go with whatever you want, right? In this talk, we are going to be using Beast, MySQL, and Asio, just because examples are like better, are more fun. But all the concepts you're gonna learn apply to both. So don't worry. Now, I hate writing coroutines which are foo and bar, and so I like writing real code, and that's what we're going to be writing here. This is the example we're going to use. This is toy. We're not going to be writing like a production-ready HTTP server, but it's enough for us to reason. So we're going to be writing the box in the middle, the server. We're going to be accepting a request from the client, and to satisfy this request, we need to access an external service. So we need to perform I/O to compose the response, right? Getting into something more real, the server is going to be HTTP, just because it's ubiquitous everywhere, and the external server is going to be a MySQL server, just because I wrote Boost MySQL and I know it. So the client is going to send us an ID value in its request, in the URL. We're going to compose a query using this value, send it to the server. The server is going to send us rows, and with that, we are going to compose important business information that we are going to return to the client, like this correlation there. Again, the example is a bit toyish, but it's enough to demonstrate the concepts. Now, wise man once told me a very important thing, which is please write pseudocode before writing code. And this is what more or less an HTTP server looks like. So we need something that, like, HTTP is based on TCP. So we need something that lets us accept incoming client connections. And I'm going to call this object TCP acceptor, just because Asio uses similar terminology. And in a loop, I'm going to wait for a client to connect. Then I'm going to handle this client. To handle this client, I'm going to read a request, query my database, and compose a response. Those of you who know a lot of HTTP may notice that this is not handling HTTP keep alive, which is an HTTP 1.1 thing. But since this is a toy, I don't really care. This is what we're going to be implementing, right? Everyone ready to see the code? Now, it might come for you to a surprise that I talk about asynchronous and coroutines. First line of code doesn't have neither coroutines nor asynchronous functions. And the point here is that I like it this way because synchronous functions are usually easier to use. So I like first prototyping with synchronous functions and then migrating everything to asynchronous. That's what we're going to be doing in this talk. So this is more or less implementing the pseudocode we had in the previous slide. We have a lot of things here, and we're going to be explaining them. First thing, we create this thing, this I/O context. This I/O context is an instance of what Asio calls execution context, very important term. An execution context, for you to understand, is like an event loop. Heavyweight object, big object. You just create one of them per application, right? Big object that handle one per application. The next thing we're gonna do is create this acceptor, which allows us to accept connections. And this kind of objects, the acceptor, the socket, in Asio they're called I/O objects, just because they allow you to do I/O. And if you noticed, we passed the execution context as first argument to the acceptor. So what this means is that the I/O objects, which are usually much more small, more cheap to create, are using the internals of the execution context, the event loop, to do their thing. So think, for example, a socket may need the list of file descriptors that we have active to do their thing. So these are I/O objects, both the acceptor and the socket. We're setting some options. We don't care that much about this. They just allow us to listen for connections on port 8080, which is quite useful for test servers. And then in a loop, we are accepting a connection and run session. This acceptor.accept is an I/O operation. So this means that once we reach this point in the program is going to block until a client connects. Right? Everything clear until now? Yep.
We have listen and we have accept.
Yes, so listen enables this is like inherited from the BCD sockets API. Listen is not an I/O, it just performs some system calls, but it doesn't block. So listen is something you need to do once per acceptor, and then you accept, you call it in a loop, right? Now, let's go with the run session. I know this looks like a lot of code. Don't freak out. We're going to explain this little by little. So the first thing we do is we create an HTTP request, and we call this HTTP read function. This reads a message from the socket into the request. So when you see this HTTP thing, this comes from Boost. This HTTP read is what Asio terms a composed I/O operation. Composed means that it's implemented in terms of one or more smaller I/O operations. So this makes sense. To read an entire HTTP message, which may be very long, you may have to call socket.read a lot of times. All the operations that are with the arrow are composed I/O operations. The term is important. Okay, more or less clear. We read the message. Then we connect to our database. This just provides the username, the password, and the database. Never embed a password in code. This is just for testing. And we execute the query into the result. This function will take care of not doing any SQL injection, and it's secure to use. Now, I want to call your attention on this sock.getExecutor, which introduces a new concept, which are executors. So you remember what an execution context was, the big I/O, the big event loop. So an executor is a lightweight handle into this execution context. So it's something that is kind of similar to a pointer. It's a little bit more, it has some extra properties. We're not going to get into that here because it can give for another talk. But so what this is really doing is it's retrieving a handle to the execution context and passing it to the new I object we're creating, so it knows how to create new I objects. If it has the execution context, it can create new sockets and new timers. Right? We are now saying if we found rows, we compose the response, otherwise 404. Nothing to see here. And finally, we are doing an HTTP write, which takes a message object and writes it to the network. And these three methods are just some bookkeeping methods that Beast needs. Clear until now? Right. Actually, this has a very big problem. And it doesn't follow really what we wrote in the pseudocode. Can someone spot it? I don't have stress balls, but can someone spot it? No? No one? Okay. So we accept a new connection and then we call run session. And we're using blocking functions. So until the session doesn't finish, we don't get back to accepting new connections. So imagine that you're in a restaurant, and once the first person gets into the restaurant and sits down, the restaurant stops attending anyone else. And if you go there, you will get ignored until the first person ends eating, pays, and leaves. And then it attends to the new person. So this is like, it would be a mad restaurant, right? This is kind of what we're doing here. I'm going to refer this to the restaurant problem. We are blocking and we're not accepting new connections. What we should be doing is launching this run session in the background. Problem, we're in a synchronous world and we have header limitation. If we want to do this with synchronous functions, you need to start creating threads. Since this is a talk about coroutines, we're not going to be doing that. We're going to migrate all our programs to being asynchronous. We could use callbacks, but that's not what the talk is about, and it distorts the code flow a lot. So we are going to be using coroutines. So don't freak out, it's gonna be much easier than what you think. So in your right, you have what we already wrote, the synchronous version. And on the left, we have the asynchronous equivalent. This works, this is actual Asio code, I've built this. So I want you to notice the differences, which aren't really that many, between this and this. So first one is the return type. Instead of returning void, I'm returning Asio waitable of void. So the actual return type of the coroutine is this template argument. Next thing, all the IO functions, yes, I've replaced them with the asynchronous equivalents. So instead of HTTP read, I have HTTP async read. And instead of having nothing here, I have these co-await keywords. Not that difficult, right? So my point here is that if you have a synchronous function written in Asio, it can be trivially converted to a coroutine by applying a set of mechanical transformations. It's not that difficult. Now, they look very similar, but they are actually very different things. So how does it work? Once I start executing a coroutine, it will execute all these lines until the first asynchronous function. Once I get here, the asynchronous function starts, it will be launched, but it won't wait for it. The coroutine will get suspended, which means that all these variables will be saved in this kind of data structure, the coroutine frame that many other talks have talked about. It will get suspended and control will return to the execution context, to the event loop. Then the event loop will take care of doing something else. Maybe it will take another session, another coroutine, and start running. Maybe it has some pending callbacks and it will execute them. But something else. Now, when the async read completes, it will notify the execution context and will say, hey, I have a coroutine to resume. It will call resume on the coroutine handle, and execution will continue after this. So to this function, pass ID. This is, by the way, just a string manipulation. I didn't show it because it was pretty trivial. And it will continue until the next co-await, and on and on and on. And this is how you write coroutines in Asio, right? Easy. Right, let's do the main. You know that main can't be a coroutine. Mains are synchronous. So how do we bridge these two worlds? I've refactored most of the main into a run server function. It has almost everything except a couple of things. So I set the acceptor, and then I have this loop. First thing I want to call your attention on is this strange construct we have here. This co-await, this coro executor. You remember the socket.getExecutor that retrieved the executor from associated to a socket? Well, this is the same for coroutines. It just has a little bit stranger syntax because coroutines are strange on their own, right? But what I mean is that this is not waiting for anything. This is not performing I/O. This is just retrieving the executor associated to the current coroutine. So I can build my I/O object, nothing else. Now, the listen method. The listen method is not an I/O method. So I don't have a sync listen because it doesn't block. I just have listen. But accept was an I/O method. So I have a sync accept. I go await it, I get a socket, so I can talk to the client and then run this run session. So this run session was the function we wrote in the previous slide, and I can co-await functions I write. So I can build abstractions. Finally, in main, I create my execution context as I did before, and then I use this function postpone. Please remember it, it's very important. We're gonna come across it a lot in this talk. Takes 3 arguments. the execution context or executor where I want to spawn the coroutine, the actual coroutine to run, which is in the form of an awaitable. So you call the coroutine, but don't co-await it. And finally, a callback that is executed once the coroutine finishes. I'm just rethrowing the exception. So if the coroutine has an exception, I just terminate. Important. Call spawn doesn't wait for the coroutine to finish. It doesn't run the coroutine. It just schedules it. So it says, hey, Mr. Execution Context, please run this coroutine when you can, and continues with its life, right? All the things happen in the ctx.run. ctx.run runs the actual event loop. You just need this for asynchronous programs. It runs the event loop, so it will start saying, hey, I have a coroutine to execute, and start executing it. And it will run forever because we have a while true loop here, so until you hit Control-C. Right, this is our asynchronous program. Did we solve the restaurant problem? Who thinks we did? Raise your hand. Who thinks we didn't? And the rest has no clue, right? Well, actually we didn't, because we are co-awaiting the coroutine. So we wait here for a client to connect, then we wait for the session to end. So we have the exact same problem. However, this time it's much easier to solve. Do you know a function that starts executing a coroutine but doesn't wait for it? Can anyone point? Maybe call spawn? Yes. So what we need to do is don't co-await the coroutine. We need to call spawn again. Again, 3 arguments. The execution context or executor that we need to use, it's always the same. The coroutine we want, and the callback. I'm not rethrowing this time. If a client gets an exception, don't affect the others. So this is it. This works. This is a proper HTTP client. Are we done? Well, I promised talking about 3 things, right? We just talked about the first one. So let's do timeouts. It's very common in asynchronous programs that you don't want these asynchronous things to take forever. So imagine if you had a network fault or a misbehaving client. This async read may take very, very long. And this is usually not good. Or if the database is down, maybe this async connect takes more time than what it should. So it's usually a common requirement to say, hey, please limit the lifetime of this async operation to just, for example, 30 seconds to a timeout. Now, this used to be something very, very difficult to do in Asio. But since 2 releases ago, it's gone much, much, much more simple. And it's just adding this extra thing, which we're going to explain in the next slide, is a completion token to the end, as this last argument. So this is it. This is how you do timeouts in Asio right now. Simple. I want to highlight what happens when things go wrong here. So imagine this async read doesn't complete by 30 seconds. What's going to happen is that Asio is going to, we're going to see it in a later slide, but it's going to time the time it takes for the operation to complete. If it doesn't complete in 30 seconds, it's going to cancel it. And if it gets canceled, it fails as if it had a network error. The behavior is very similar to a network error. It will fail with this error code, with operation aborted. So for a network error, you may have like end of file or network reset. And for cancellations, you have operation aborted. Important, it doesn't schedule anything. The coroutine will keep executing. It doesn't remove tasks from the IO context or nothing. It's nothing weird. It just behaves as a network error. With this setup we have here, Asio converts any error codes to exceptions. So if we get a timeout, same if we get a network error, this co-await will throw. The co-await expression will throw. There are ways to prevent this. I don't have them in this presentation, but I can tell you afterwards if you're interested in that. Right? Clear until here? Pretty easy how to set timeouts. Now, we get with completion tokens. This may be the most important slide you're going to have, so please pay attention. What the hell is a completion token? If you hit go to the definition to one of these async whatever things in Beast or in Asio or in MySQL, they're pretty much the same, you would have this kind of thing. I've simplified things a lot because in Beast things are very templated, but it's enough for what we need. Some terminology. Asio calls these initiation functions. And this makes a lot of sense because they're initiating an asynchronous operation. So initiation function, right? And we have this final completion token argument, which is Asio deferred. This completion token is going to determine us the completion style we want to use. So do we want to use coroutines? Do you want to use callbacks? Do you want to use something else? And it's going to allow us to customize a lot of things about the asynchronous operation. For example, do we want a timeout for the operation? Do we want to make it thread safe? So a completion token is really a customization point. If you say nothing, remember the first slides, we didn't have any completion token at the end. If we say nothing, we get what we call the default completion token, which is something pretty recent too. And at this point, most of the operations have this Asio deferred thing. Asio deferred tells Asio, well, I want the operation to be packed into something I can co-await. So we can use everything that is Asio deferred with coroutines, right? Now, this and this are equivalent because of this. This tells Asio, I want to use coroutines, but by the way, also set a timeout of 30 seconds to the operation. But that's not the only way we can do with async write. We can also use callbacks. And actually, so Asio deferred is a completion token. Cancel after is a completion token too. Callbacks are valid completion tokens, and this is perfectly valid. What's going to happen is it's going to launch the operation, the callback will be called after the operation completes. But actually, this is valid too. This is very useful when you have like half of your application is legacy and it's doing sync, and you want to introduce Asio, which does async, and you want to communicate them via, for example, std futures. So this tells Asio, hey, please package my operation into something that when I call get will block my current thread until the operation completes. So that's not super relevant, but what I mean is that you can customize the completion style you want to use, so either coroutines, callbacks, features, or whatever, by using different completion tokens. And actually, this O2 is very relevant because the return type of the initiation function changes with completion token. In Asio deferred, something we can call await. In the callback, void. In the use feature, std feature, right? And this brings us to the universal async model. So what's this? An operation, a composed operation, or an IO operation is said to comply with the universal model if we can do this, if it supports arbitrary completion tokens. So these operations are super handy because I can use them, like they're super versatile. I can set timeouts to it. I can, if I want, I'm C++11, I can use callbacks. If I'm in C++20, I can use coroutines. But they're very difficult to write. They are a pain to write. So don't try that at home. And the cool thing about completion tokens is that they're orthogonal to IO operations. So this is kind of a similar relationship to in STL from iterators and algorithms. Once you learn how to use a completion token, you carry your information for whatever library you want to use. So if you learn today how to use cancel after, you can use it with Asio, with standalone Asio, with Boost.Asio, with Beast, with MySQL, with everything. So it's knowledge you can apply to many different things. And if I write tomorrow Boost Postgres, you will be able to use this. And this is the cool thing. Any questions about completion tokens? Yeah?
Yes. So when you're using the future as the completion token, yes, how can you forward the errors?
By default, if the operation fails, an exception will be thrown. I can show you after the talk. I have a bonus slide. You can use another completion token to say, Asio, hey, please don't do this of throwing exceptions, and then you will get a tuple of an error code and a size t. And this same thing applies for coroutines too. It's called as-tuple. Right? Cool. Adapter tokens. This is a special kind of completion tokens of which cancel after is an example. And you may have noticed that really cancel after doesn't say I want to use coroutines or I want to use callbacks. It doesn't specify the completion style. It just says 30 seconds, please. And
Rubén, we've got one more question.
Oh, sorry. Yes.
Yeah, on the previous slide, is there a way to combine callback with the cancel after thing?
with the, yes, and this is my next slide. Don't get
Amazing.
fooled. Yes. It's the,
Unless it's a clarifying question, wait until the end. Asynchronously wait.
well, now, the point of these kind of tokens is that they wrap other tokens. So this is why they're called adapter tokens. As anything in Asio right now, the default is deferred. So these and these are equivalent. So this says, cancel after really says, hey, apply me a timeout of 30 seconds and do whatever the underlying token wants. So I can do this, 30 seconds, but don't use coroutines. I'm in C++11. I want to use callbacks. Okay, you can, or I don't like coroutines for whatever reason. You can use callbacks. This works. So whatever you learn here today about cancel after, you can do with callbacks, you can do with features, you can do with fibers, with whatever underlying completion style you want. You can even stack these kind of completion tokens. If you have as tuple to prevent exceptions, you can say cancel after, as tuple, deferred, and stack things. Right? Which gets to the third point, cancellation. So there is a reason why this is called cancel after and not timeout, and it's because at the heart of cancel after, it's the cancellation model. These slides are gonna be a little bit more abstract, so if you fall asleep, please yell. When I'm gonna teach you what happens when cancel after is called, because it's good for you to know, especially when things go wrong, it's important to know how this works. When Asio cancel after, an operation using Asio cancel after starts, it creates an object, which is a state, this kind of state. And it has really two things. Well, many things, but the operation and a timer. What's a timer? A timer is an IO object that Asio has to implement asynchronous waits. So it's the asynchronous equivalent of this thread sleep4, right? Easy. And it's gonna launch the two things in parallel. So here is my operation. That would be my HTTP async write in my example. And the timer. Time goes down, and this is the 30 seconds deadline we had. This is the sunny day case. Everything went right, and the operation finished before the timer. So the timer gets cancelled, and everything is fine. But what happens when things go wrong, and the operation doesn't finish on time? So in this case, the timer fires, and it's gonna try to cancel the operation. And hopefully, this yields an error code of operation aborted. Now, this cancellation is easy because timers have a .cancel method. Nothing to see here. But the operation is much more involved because Asio cancel after can be used with whatever operation you want. So Asio needs a generic cancellation mechanism that is able to cancel whatever you pass it. And that's not easy. It didn't exist until some releases ago. So that's what the per operation cancellation mechanism is about and what we're going to explain in next slides. As I had already said, two types of cancellation in Asio. Object-wide cancellation, this has been there since release number 1. It's some IO objects have a .cancel method. We just say sock.cancel, and any outstanding async operations the socket has get cancelled. Point here is that if you want to cancel a specific operation, imagine you have a read and a write on a socket, you can't. This cancels both. And it understands nothing of composed operations. So there is no, it acts on IO objects, not on operations. So this has a lot of limitations. It's good if you can use it, but it's not enough to implement cancel after. So this is why Chris did this per operation cancellation thing. It's a much more involved mechanism. It's signal slots, and the cool thing is that it can target whatever operation you want. So if you have a composed operation like HTTP async write, you can cancel it with that. Now, friendly reminder, if you want cancellation, you need to go async. You can't cancel sync things. So now that you have coroutines, please use them and don't come creating 100 threads. Now, these are a bit of the internals of Asio cancel after. You are not going to be using this directly ever, hopefully. This is just for you to understand what's going on. So please don't create cancel signals on your code. This is just for you to understand. As all signal slot mechanism, this has two ends. The signal is the owning one, and it owns a function, which is a cancellation handler. We're going to see it in a minute. And the cancellation slot is non-owning. It's just a pointer to the cancellation signal. This has two ends. one end for the operation. So when an HTTP async write starts executing, it will propagate this cancellation slot until the bottommost operation, that may be this one, socket write. And this socket write is going to set the cancellation handler to say, hey, when you need to cancel me, this is what you need to call. So for example, imagine you're in Windows and async write sum says, hey, if you need to cancel me, you need to call cancel.io x with this handle value. Then maybe the next operation comes, the handle gets replaced and is, hey, I'm now on another socket, I'm doing a read. You need to call cancel.io x with this other handle value. And this is what the cancellation handler is. So the operation end, and then you have emit. Emit is just requesting to cancel an operation. You say, hey, please cancel. And this is what cancel after the state uses to perform the cancellation. I know this is very abstract, so we're going to see a nice flow diagram to demonstrate it. Remember the cancel state, the cancel after state? We had operation, the timer. Now we know that it also has a cancellation signal. This, as we said, launches two things in parallel, the wait and the write. The write is a composed IO operation, remember? This means that it is implemented in terms of one or more of these smaller operations. It's async write sum. Through a mechanism we don't really care much about, these handlers are like function objects, but they have like special properties that Asio uses. And one of these properties is the cancellation slot. This async write sum gets called with a handler, and this handler has the property of the cancellation slot. So this is pointing to this, right? The cancellation slot gets here, and it calls in play. So this says, hey, I am starting an async write sum, so if you need to cancel me, please call this function, this cancel.io x or whatever. Now, things go wrong, the timer expires, and emit gets called. So the handler gets called, and this will just make the operation fail. Now, I know this is a lot of things. You don't really need to learn all this. What I want to transmit you with this is that cancellation always targets, it's not magic. It just targets the bottommost operation. It doesn't make the coroutine stop executing or anything weird like that. It just makes the operation fail because it invokes the relevant APIs to make it happen. So this is what cancellation more or less is about. Is everyone alive? Anyone has any questions? Right, let's return to something more joyful, if you like. Now, this was our program with coroutines. We have these cancel afters scattered all over the place. The cancel after in the read and the write are very reasonable. But these two, it's still a bit weird that we're setting individual timeouts for connect and execute. Because, okay, now we have 2. So the maximum timeout, let's say, is 60. But imagine we have 10 operations because we need to consult a lot of external services. This is a mess. Like, we can't just set the whole timeout would be like 5 minutes. Doesn't make any sense. So what we really want is to say, hey, apply a timeout, but just to this. Right? To what I'm pointing here. To these two operations, to the whole database thing. Can we do that? Well, actually, we can't set a timeout to a portion of a coroutine. This is nothing. But we can set a timeout to a whole coroutine. So we're going to do a little bit of refactor, our fun part. So first, we remove the timeouts from the operations. Then we take all this code, which is really handling the request, and take it to a separate function, a separate coroutine. I'm not going to show it because it's just cutting the code and pasting it. Nothing special. So we have this handle request, taking the ID we want to look in the database and returning the response. We're going to put it into a function and refactor it. So we have this code. Now, can we set a timeout to this? As it's written, we can't. There is no way to pass a cancel after here because that's a function we have written. Does this function follow the universal async model? Who think it does? Raise your hands. Well, it doesn't, because you can't pass a completion token here. The handle request is something we wrote, and it just uses coroutines. So you can't use callbacks with that. You call wait, period. So we need a function that runs a coroutine and allows us passing things. Does anyone have any idea what we could use? Yes, cospawn, that's it. So this is the cospawn we had in main. Remember it? 3 arguments: the execution context, the thing we want to write, and a callback that executes when the coroutine finishes. Now, if you've paid attention to my cancellation, to my completion token slide, this thing may start looking you as a completion token. And I actually didn't tell you the full story there. You can pass here a callback, and this is true, but you can pass different things here. This is cospawn actually does follow the universal model, so you can pass here whatever you want. You can pass in a callback, you can pass here Async deferred, you can pass use future, whatever you want. And it turns out you can also pass cancel after. So when we can actually write this, and this will do exactly what it says. It will set a timeout to the entire operation, to the entire coroutine. We will have a diagram much more complex than it's the same diagram we had in the previous slide about the signals and the slots. It will be much more complex, but it will boil down to the same thing. It will do the same thing. When the timer expires, it will cancel the bottommost operations, and then it will go all up and make the coroutine fail. So congratulations for making this far alive, if everyone is. I want to thank the C++ Alliance for sponsoring this talk. I left you 2 links here. This one contains the code I used for the slides. I'm going to upload the slides in PDF. It's not there yet, but it's there. And this QR code and this link are for a chat application I wrote using C++ 20 coroutines and Asio and MySQL and that. This is actually a live demo. I hope it works. I haven't checked it just yesterday. I think it does. The point is that if you want to see something more realistic that does HTTP and does Redis, does MySQL, does JSON, does almost all Boost, you can check this link, and I think it can be used as reference to learn a lot. Sorry.
Thank you. Thank you very much. We have time for questions.
Thank you very much for the talk. When you sell when a coroutine is cancelled, what you mean is, for example, you're reading a file.
Yes.
And the file, you expect it to be read in about, 30 seconds.
Yeah.
But somehow, I don't know, the connection is of the network is unstable or whatever, and it takes much longer, like, 5 minutes. It's going to spend those 5 minutes, right?
You mean that
That the coroutine is going to keep reading the file?
So if you don't have the cancel after, yes, it's going. So if you have,
I mean, if you have the cancel after.
If you have the cancel after, no, the coroutine will issue the cancellation, and in 30 seconds it will just return with the operation aborted error code. So it won't continue reading the file. Depending on the operating system, and they have different capabilities. I know for sure in Windows it cancels the thing and it aborts it. I don't know in Unix how it does it. I think it depends on whether you choose IO, uring, or EPOL.
Okay, so at that point, I think.
But once
you rely on the operating system to just cancel.
No,
that.
but even in Linux, if the IO context, if the operation stays lying there, it will be the problem of the IO context. The coroutine will return in 30 seconds.
Okay, perfect. Thank you.
That was a synchronous answer.
Can you go to, I think it's 13? 3 before that?
Yeah.
Okay, so this is the same question I did yesterday for Dietmar. This context run can be executed through several threads?
Yes. So IO context is a thread-safe object. So you can make this a multi-threaded. All I've done is single-threaded because it's just simpler. You can spawn like a vector of threads and then make all of them call run, and it will be asynchronous. However, Two things. If you are doing that, instead of an IO context, you may want a thread pool. This is another execution context which will just create the thread for you, and it's just much easier.
Okay.
But you need to take special care because threads introduce race conditions. So you need to take care of not making race conditions. There is a special kind of executor in Async which is called a strand that allows you to protect shared data structures without using std mutex. Never use std mutexes if you're writing asynchronous Async code. Please don't use strands. And getting strands right is extremely complex. Use thread sanitizer always, and first measure. If you're enough with one thread, do it. Second thing you can do if you're low on performance, you can create a thread pool outside of and make heavyweight operations running this. Imagine you are doing a super heavy calculation. You are, for example, hashing passwords, which is by design very heavy. You can offload that to a separate execution context, which I can teach you afterwards how to do, and so you don't overload the main thread. And if you don't, you can try either making like several threads there or making one context per thread, which you need some special structure. I haven't really done it before, but I know you can do it. So yes, answering your question, yes, but you need to take some special caution. Like, I don't know if we have a lot of, I don't think this really would, I want to go to slide. Okay, you need to take special care with this because cancel after does parallel operations. So it may happen that one thread is running the callbacks associated to this operation, and at the same time, another thread is running callbacks associated to the timer, and you get a race condition. So you need to protect everything. So.
Okay, so my second question is,
yes?
How difficult is to debug all this with, coroutines and so many things?
I know there is, it's not as simple. It's simpler than with callbacks, but because the control flow is easier, but it's not as easy. I know there are some utilities, I would say in GDB, someone wrote something to make things easier, but they are not, I don't think they're straightforward to use at this point. So my hope is that it will get better in a year or something. But at this point it's not that good. Because you will see the stack you will see is not really what you expect. You won't see this is awaiting this and this is awaiting this. You will see the IO context called resume and this called another resume, and you will see strange things.
That's the actual question. Yeah. If I can see all the variables in a nice
it's still
way.
much easier than if you just did the fjum context thing we used to do in C++11.
Okay, thank you.
More questions?
Thanks for the talk. I enjoyed it a lot. So my question is, under which situations you may expect that some completion tokens may imply some overhead? So I'm thinking about, for example, if you create too many timeouts, maybe you could expect some kind of overhead.
It depends a lot of the completion token. Actually, I don't think the completion token itself brings any overhead. But for example, when you do this Async cancel after thing, you are creating a timer, and this probably yields a memory allocation. I didn't tell you the full part of the story. Async cancel after has another overload taking a timer, so you can reuse a timer. So if like in my code, I tend to just write a timer per session and then reuse it over and over, so you don't recreate it again. But it just was easier for the talk doing this. Regarding as tuple, I don't think it has any overhead. Coroutines, well, you have the coroutine frame allocation, which is there, but when you do callbacks, you actually do also allocations. So I don't know. It's for sure if you are doing, you are not under heavy load, synchronous is usually a little bit faster, not perceived, it's a little bit, but you can't do timeouts with synchronous. So if you need timeouts, yeah, that's that.
Okay, thank you. Yeah, thank you so much.
I had a question about slide 26.
About?
Slide 26.
Slide
26.
26.
20.
Okay. Sorry, I'm deaf. Okay.
So here you're grouping some operations under this handle request. Is there any way to know which one failed? Because I'm thinking, if you have two different asynchronous tasks that talk to a database and one of them fails, you want the other one to be consistent. So you kind of need to undo whatever the one that succeeded did,
Okay. If you want to do this, you would handle this the same as if a network operation failed. So actually, I have a bonus slide which may be useful at this point. This is how you avoid exceptions. You are gonna actually this is you are gonna need this as tuple, because if you have an exception, well, you can do a try catch.
Right, but I'm thinking the failure, like it happens on the outside of the handle request.
You will see it in the you will see. Once. So say I don't have the actual, but say that async connect was the one that failed. You will see in the inner function in the handle request, you will see async connect failing with operation aborted.
Okay.
This is what I mean that it targets the bottommost operation. The cancel after, you will see the error in the actual async connect.
And then would it also fail the next thing because already the timeout has happened, or?
Coroutines have a thing which is throw if cancelled. And just for coroutines, if you don't, there is like a cancel state for coroutines. It's even more complex than what I told you, but there is they hold like a state thing where they store if they were cancelled or not. So if you do nothing, the next time you start an asynchronous operation, they throw an exception. Okay. But you can disable that.
What happens when you disable it?
You do co-await Asio this coroutine throw if cancelled, and you pass false.
Okay.
I can, if you bring come here after the talk, I can teach you how to.
Right. Thank you.
Do it.
Thank you. More questions? I see none. So thank you very much. There was any? Thank you very much, Rubén.